working in a coal mine, going down, 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 working in a coal mine. About to step.
Let's move on to problem 5.2. What we're going to do here is start using our knowledge about the normal distribution and the cumulative probabilities and standardizing with the z-score to calculate some probabilities of certain events based on the overall population of that event being normally distributed. So problem 2 says, suppose it is known that the distribution of purchase amounts by customers entering a popular retail store is approximately normal, with mean 75 and standard deviation $20. And then we're going to calculate probabilities of a bunch of different events. So first off, let's just write this down. We've got mean of $75 and standard deviation, which I'll call sigma from now on, of 20. And we could put the okay, then part A says, what is the probability that a randomly selected customer spends less than $85 at the store? So in A, I'm going to write down what we're looking for, probability of a random customer spending less than 85. And let me widen up column A so we can read this. Okay, now we're going to have Excel do the work for us. That's the whole rationale of Excel. But just to remind us what Excel is doing here, let's go back for a minute to this idea of the standard normal distribution in z-scores. And remember, the standard normal distribution is defined as mean of 0 and sigma of 1. So we're putting everything, we're basically refining this to say adjust the sigma to 1, and how many standard deviations does the value 85 represent, and then we can easily find the probability based on our z-table to the left of that. Okay, so to find the z-score then, remember z is x minus mu over sigma, and here our x is 85, mu is 75, sigma is 20, so that's 10 over 20, or 1/2. So what we're saying here, okay, the z-score of 0.5, what we're saying is $85 in this distribution is 1/2 a standard deviation to the right. So now I'm saying what percent of observations are to the left of that value of 0.5 sigma. Old school way is to go back here and find 0.50, and there it is, 69.15%. I'll write that down. In fact, I'm going to say 69.15%. Done the old-fashioned way, working everything out by hand, but that's not what Excel is for. Let's use Excel, and the function we're going to use here is called the norm.dist. So let me just show you. Equals norm.dist. And notice what it says here. It says returns the normal distribution for the specified mean and the standard deviation. And really what that should say is that it returns, it standardizes it and then gives us the probability. 3 arguments. First is the x, the specified value, that's 85. I'm sorry. The mean, we can do this by cell reference here, B2. And the standard deviation we can also do by cell reference, B3. And then cumulative, okay, what do we want? Do we want a cumulative distribution function or the probability mass function? We want the cumulative distribution function. True. Okay, so we need to put true in there. And then, hey, look, 69.14. If we round that to 4 decimals, 69.15, and let's convert it to a percent with 2 decimals. 69.15. Hey, that's Excel doing the math for us, right? So that's pretty snazzy. So let's keep moving on, and I think the rest of this problem is going to be really easy. Okay, B says, what is the probability that a randomly selected customer spends between $65 and $85 at the store? I just want to show you how tricky and tedious this is to do manually, because what we're doing here now is saying, okay, so for between 85, which we know is 1/2 a sigma, 0.5 in z-score terms to the right, and then 65, which when we calculate that z, okay, x minus mu over sigma, which is going to be 65 minus 75 over 20, and that's going to be minus 10 over 20, so that's going to be minus 0.5. So that's going to be minus 0.5 sigma to the left. What we have to do is we want the probability that the value selected at random lies between there. So what we're going to do is take the probability of this and then subtract the probability of this. And actually the probability of what's to the left of this value is only this stuff here and the tail. And the way we would do that is we would say, well, that's 1 minus the probability of of less than 65, we're dealing with only what's called a one-tailed z-table. So, and because the sigma is the same, we can say that's the same as the probability of what's 1 minus the probability of less than 85, which equals 100% minus the 69.15. Okay, that which equals 30.85%. Okay, so this, what I'm saying here is the probability of stuff being in this little tail over here is 30.85%, because the cumulative is 100%. The stuff in yellow now, stuff in here is going to be the probability of this percent probability number minus this percent probability number, and that works out to 38.3%. Okay, that was kind of confusing and kind of tedious, wasn't it? Let's see if we can make our lives much easier by having Excel do that calculation for us. So I'm going to start off. I want to enter in the probability distribution. So I'm going to do norm.dist for the first value, which was, remember, 85. Okay, the mean 75, standard deviation is 20. I could type them in or do cell reference, doesn't really matter. And then true. Okay, and then we're subtracting from that the norm dist of 65 for our x, 75 for our mean, 25 for our sigma again, and true. Okay, it needs to put another outer bracket. It fixed it for me. Hey, 39.29, 39.3%. Right. So if we know what we're doing, we don't have to engage in a lot of tedious calculation. We can have Excel do it for us. Okay, now I'm going to leave you to do C on your own, because that's going to be exactly like A, although I'll give you one hint. We're not looking at the area to the left of 85. Once we find the z-score, we're looking at the area to the right of 45. But just note here that the area to the right, and this 45 is going to be out here somewhere. The area to the right of 45 would be the equivalent of the area to the left of, well, whatever's 75 minus 45, whatever's $30 to the, so 45 is $30 to the left of the mean. So the area to the right of that would be equivalent to whatever's $30 to the right of the mean. So if I add 30 to 75, I'm looking at 105. Okay, so I'm thinking about whatever's to the left of 105. The probability is functionally equivalent to whatever's to the right of 45. So if you find your z-score based on 105, you'll be all set. Okay, now we're moving on to D, and D says find the dollar amount such that 75% of all customers spend no more than this amount. Okay, interesting. I'm kind of doing the opposite now. We're not taking a dollar amount and finding a probability. We're taking a probability and finding a dollar amount. But let's write down what we're looking for, as always. And what I'm looking for is the dollar value at greater than 75% of the distribution. Okay, now mathematically, how are we going to work that? First off, I need to go back to my z-table, and instead of having a z-score and finding the percentage, I have to find the percentage that's closest to 75, and where's that going to be? Well, look, it's going to be here. Here's 74.5, 74.8, 75.1. So it's going to be somewhere between here and here, and without more decimal places in my z-table, this is about as close as I can do. We could technically use a method called interpolating to find the exact value by kind of finding ratios between these numbers, but we don't need to mess with that. We'll just kind of split the difference. So the z-score there is going to be 0.6, and then something between 7 and 8 in the 100th place. So let's call it 0.675. So I use my z-table going kind of in the other direction. I know the probability, now I'm finding the z-score. So back here I'm going to say I know my z is 0.675 at this probability up here. And that's, by the way, because this is 1 sigma, this is 0.675 sigma, so now I'm somewhere in here. I'm about 2/3 of the way between the mean and 1 sigma. And we're saying and we know the probability in this range of the distribution is 75%. And we know the z value associated with this point. And all we got to do is use some algebra to calculate the value of x here, the dollar value in this case. So, z equals x minus mu over sigma. Z is 0.675. My x, my unknown, is the only thing I don't know. My mean is 75. So I'm going to plug in all the values I know. And what does this work out to? I'm going to multiply each side by 20, use some simple algebra. 20 times 0.675, 13.5. So I got 13.5 equals x minus 75. Now let's just add here to isolate x, plus 75, plus 75. And I've got, what is that, 88.5 equals x. And this is dollars. So I know my answer here by doing it the old-fashioned way. Again, you don't have to do it this way. I'm just showing you what Excel is doing for us. As long as we understand what's going on, we can tell Excel to do the calculations, and it's lickety-split. So now what's the tool we're going to use? Remember, when we have a value here and want the probability, we use the norm.dist formula in Excel. What about when we have the probability and we want the value? We're going to use a related function, norm.inv. You'll notice it's the next thing down. Okay, and it says returns the inverse of the normal cumulative distribution for the specified mean and standard deviation. So the arguments here, this is the probability, 0.75. Now here, enter it as a p-value. Do not enter it as a percentage. So use a decimal. 0.75, the mean. We can use cell reference or we can type them in. Doesn't matter. Standard deviation. And bada boom, 88.489. Let's format that as dollars and round it to the 2, which it does automatically. 88.49. I calculated 88.5 manually. The only reason we're off by a penny is because, remember, I had to interpolate. So I just split the difference, which isn't the most accurate way to do it, based on the fact that my Z table I'm using only goes to hundredths. But close enough, and Excel, of course, is going to be perfectly accurate and much easier to calculate. Okay, so now E. Find the dollar amount such that 80% of all customers spend at least this amount. Well, I'll leave that for you to do on your own. That's going to be very similar to what we just did in D using the norm.inv functionality. But again, last time we were looking for what was to the left of 75%. Now we're looking at what's to the right of 80%. So whatever's to the right of 80%, let me just give you another hint. Okay, let's say 80% is going to be out here somewhere at whatever sigma value that is, whatever z-score that is. Whatever's to the right of that out here would be equivalent to that flipped symmetrically over the mean, whatever's to the left of minus that. So once we find in our z table, you know, if we were doing it the old-fashioned way, the p of 80%, and then that corresponding sigma, we just change the sign of that to find whatever's to the left of that would be equivalent to whatever's to the right of this. Okay, now finally we'll do F together. This is kind of fun, just kind of a little challenge that helps us really guarantee that we conceptually understand how to work with this idea of the normal distribution z-scores. It says find two dollar amounts equidistant from the mean such that 90% of all customer purchases are between these values. Okay, I'm going to go back and kind of clean this up here. It says we want 90% between two values. Well, it's going to be slightly less than 2 sigma on either side, isn't it? Because 2 sigma on either side by the empirical rule gives us 95.5%. It's going to be close, but not quite 2 sigma on either side. But we need dollar values. So how are we going to figure this out? Well, and we're looking for this this cumulative area between those values. Well, what do I know about 90%? I know that my mean is 50%, right? So if I want 90%, that's if I want the middle 90%, I'm basically going from the mean, and I'm finding 45% on the right and 45% on the left. So I'm looking for a chunk that's 45% on the left-hand side of the mean and a chunk that's 45% on the right-hand side of the mean. Well, working from the mean up, the boundary on the right-hand side is going to be 50 plus 45, which is going to be 95%. And the boundary over here on the left-hand side is going to be 50 minus 45, which is going to be 5%. So what I can do is I could simply take I could invert and find my value here, and then the same thing here. So I could do two calculations doing norm inverse, and that would get it, and we'll try that here in a second. another thing I could do, now if I was doing this the old-fashioned way, what I'd do is I'd have to go back to my Z table and find 95%. I have to go back to my Z table and find 95%. Now where is 95%? 95% is going to be somewhere pretty much halfway in between these two values here. So I could just take the midpoint, 1.645. So I know my Z up here equals 1.645. Yeah, and that makes sense. We said, remember, it's not going to be quite 2 sigma. It's kind of close, but not quite 2 sigma to the right. And then I could use that. I could solve for Z. Remember, Z equals x minus mu over sigma. Well, that's going to be 1.645 equals x minus 75 over 20. And if I multiply out the 20, kind of like what we did earlier, I get 32.9 here equals x minus 75 plus add the 75 back and I'm going to wind up with, that's a plus sign, 32.9 plus 75, that's 107.9 equals x. So the upper bound is $107.29. The lower bound, I could go through all that math again, trying to find the z-score and stuff, but I know it's basically the symmetrical value on the other side of the mean, and the mean is 75, so let's just subtract 75 from that, 107.29 minus 75. Well, hey, we just did that, right? It's 32.9. We just did the kind of the reverse of that. So over here it's 3290. Okay, so my 90% middle is bounded by 3290 on the left and 107.29 on the right. But man, look at, isn't that a mess, all that math and algebra? Isn't there a better way? Or please, Mr. Excel, do the work for us. As long as we conceptually know what's going on and what to tell Mr. Excel to do, he's going to do the work for us. So what's it going to be? Well, I could do a couple things. Like I said, first off, I think the easiest way would be to say, what is the dollar value that's greater than 95% of the distribution? And that's just going to be a norm dot inverse 0.95, mean 75, standard deviation 20. 107.9. I wrote this down over here wrong. Well, not 107.29, 107.90. There we go. And sure enough, that's what Excel calculated. That's just my boundary in my right tail. So the next thing I want to do is say a dollar value that's less than 5% of the distribution. And this is now isolating, remember, that middle 90%. So it's the same thing. Norm dot inverse 0.05 is 5%, not 0.5. Mean is 75, standard deviation is 20. And there it is, 42.9. We estimated. Excel's a little bit more precise, 42.10. Format it as money, and we're all set. Okay, problem 5.3 is kind of interesting. It says, a machine used to regulate the amount of a certain chemical dispensed in the production of a particular type of cough syrup can be set so that it discharges an average of mu milliliters of the chemical in each bottle of cough syrup. The amount of chemical placed into each bottle of cough syrup is known to have a normal distribution with a standard deviation of 0.250 milliliters. If this machine discharges more than 2 milliliters of the chemical when preparing a given bottle of this cough syrup, the bottle is considered to be unacceptable by industry standards. Determine the setting for mu so that no more than 1% of the bottles of cough syrup prepared by this machine will be rejected. Okay, and that sounds like a pretty real world type of problem. So first off, let's just conceptualize what's going on here and then think about the math we would need to solve it. And then we're going to make Mr. Excel solve this for us. So here's our normal distribution. And now mu here is unknown. We're going to dial that in, but we're going to try to dial it in to such that, and of course we do know sigma. Sigma is 0.250 milliliters. Or we could say minus sigma over here, 0.25 minus 0.250. Okay. And we're saying we do have kind of a critical value or a threshold value here. Because the problem says, okay, we don't know mu, we know sigma, but the problem says if this machine discharges more than 2 milliliters of the chemical when preparing a bottle, the bottle is considered to be unacceptable by industry standards. So we know that we've kind of got a maximum over here of 2 milliliters. So, and it says the setting for mu so that no more than 1% of the bottles of cough syrup prepared by this machine will be rejected. So we're going to put an upper limit of 2 milliliters, and we want this to be at the 99% probability distribution. So in other words, when we're looking to the left of 2 milliliters, everything out here in the rest of the distribution, that's going to be 99%. Okay, so how do we tackle this? Well, we're basically kind of working backward from the idea that we have 99%, and we know that if we have a probability, we can find a z-score. Let me take us back to my z-table for a minute. And 99%, you see I've highlighted it here. It's between 98.98% and 99.01. And again, we don't need to be totally accurate. We'll just say it's halfway between. So that would be a z value of 2.3, and then halfway between 2 and 3 in the 100. So it's 2.325. So I know z there. I can say my z value for up here equals 2.325. Okay, and from that, can I calculate a mu if I have, remember, z equals x minus mu, observation minus mean over sigma. Well, I've got my sigma, I've got that as 0.25, I've got my x, which is 2, so yeah, I can calculate my z, and that's going to look like this. Okay, but remember, we just said my z is 2.325, so that's 2.325 equals, now my x is 2 milliliters, minus the mu is unknown, over my sigma, which is 0.250. So just algebra. I'm going to first off get rid of the denominator, multiply each side by 0.250, multiply this by 0.250, and that works out to 0.581 equals 2 minus mu. Let's, a couple ways we could do this. I'll add mu to each side. So I've got 0.581 plus mu equals 2. And then when I subtract the 0.581 from each side, I wind up with mu equals 1.419. Now that if you're good with the algebra and you know how the standard normal distribution works, that actually wasn't too hard. So I got mu equals 1.419. I'm going to write that up here. But remember, we want Mr. Excel to do all this work for us. First off, let's write in here mean, and I'm just going to kind of put, I'm just going to leave it blank. We'll use cell reference. Sigma 0.250. Okay, and we're saying what we're looking for is an x that is greater than 99% of the distribution. Okay, and this goes back to problem 5.2 where we had a probability and we're trying to find a value of x. And remember how we did that? That's norm inverse. So let's try that. Norm.inv, probability 0.99. Mean, we don't know the mean, so what are we going to do? Well, we can't do this yet. We've got to solve for it. Now, if I plug in what I solved for using my z-score, 1.49, my standard deviation 0.25, now I'm pretty close to 2 there. I'm a little off probably because of rounding and my crummy interpolation of my probability from my z lookup table. But that's not the way we want to actually do this. What we want to do here is just kind of maybe let's try to plug in values of the mean and kind of guess and check, and we can get close. So I'm going to say I'm going to redo this, and instead of plugging in my solved value, I'm just going to plug in a cell reference, and we'll start guessing based on the cell reference. And let's just put 1 to start with. And I'll show you what I mean here. As we change this value by guess and check, we'll try to get closer and closer to exactly 2. So that's going to be norm.inverse, probability 0.99, mean, cell reference B2, standard deviation B3. Okay, so now I'm going to start changing this. 1.5. That gets a little too high. Okay, 1.4. A little too low. 1.45. Okay, I'm getting closer and closer. I can go 1.44. And I could basically guess and check until I got this. I want this to be like 2.00. That's going to be kind of tedious. We could get there. It probably wouldn't take too long. But check this out. Excel can actually do that for us. In other words, we can tell Excel, hey, keep plugging in numbers here, and then run this until it gets exactly to 2. And stop when you're exactly 2, and then just leave that number whatever it should be. So let me make that 1 again. I'll show you what we're going to do here. What we're going to do is something called a goal seek. This is, as they say, sick, how awesome Excel is when we know how to use these higher level functions. Okay, so notice what I did. What I'm going to do is go to Data, and then over here in What If Analysis, and I'm going to select Goal Seek. Okay, and you notice there's three things here. It says set cell, so we pick a cell that we want to find a value for to the value by changing another cell. The cell we want to set is our calculated inverse distribution, so that's going to be B5. So we want to set cell B5, and we want to set it to 2, and we're going to set that by changing B2. And look at that. Did you see that? How awesome it was? Excel dialed it in exactly for us. 1.418. That's actually much more accurate than I was able to do by kind of guessing at my z-score when I only had 2 decimal places to work with. Right? I'll walk you through that again in case you missed it. Okay, so remember, we're going to plug in values here for the mean, and we want to find whatever value of the mean gets us to a value of 2 here, representing the 99th percentile pretty much of the distribution. So I can sit here and guess and check myself. 1.5, that's a little too big. 1.4, little too small. 1.43, little too big. I want this to be exactly 2, not 2.01. That's not close enough. I want it to be 2.000 or so. So I'm going to tell Excel, okay, up here, data, what if analysis, goal seek, and I'm going to say to Excel, set the cell B5 to value 2 by changing cell B2. And I hit OK. And there we go again. Excel instantly ran a whole lot of numbers because it has a lot of computing power and found 1.418. And let me just show you that if I add decimal points to, yeah, it's exactly 2. It's not just close, that's exactly 2. That's 2 to within as many decimal points as Excel will show me. See, I keep adding decimal points all day. That's exactly right. Okay, so there we go. Used Excel's computing power to find the value, this critical value, in a realistic type of application of standard normal distribution. Okay, now problem 5.11. Now, this one I'm really excited about because I'm going to rock your world with a combination of simulation. So we're going to use some of our probability knowledge generating random numbers, and using our newfound knowledge and skills with the normal distribution to do a very realistic business problem involving something near and dear to my heart, profit maximization. And really something that I think you will find immensely practical. You might not do something exactly like this, but chances are you'll have some opportunity to do something along these lines. And as we build up your Excel skills, this is really something that you can shine with. And this is really kind of what separates the MBAs from the undergrads. So let's rock this problem. Okay, it says Matthew's Bakery prepares peanut butter cookies for sale every morning. It costs the bakery 50 cents to bake each peanut butter cookie, and each cookie is sold for $1.25. At the end of each day, the leftover cookies are discounted and sold for 40 cents per cookie. The daily demand in dozens for peanut butter cookies at this bakery is known to be normally distributed with mean 200 and standard deviation 60. Before we really do anything else, I'm going to write that down. Mean 200, sigma 60. The manager of Matthew's Bakery is trying to determine how many dozen peanut butter cookies to make each morning to maximize the product's contribution to bakery profits. Use simulation to find a very good, if not optimal, production plan. Simulation. First off, we know we want to create a lot of random numbers that will represent possible demands for the cookies, and we're going to use the parameters of this normal distribution to convert those random numbers into potential values, demand values, on the basis of the normal distribution. So before we get too far ahead of myself, let me first set up some random numbers. I think the best way to do that is just to create a column A of random numbers. Remember, Excel rand open close parentheses is going to create a number to 7 decimal places between 0 and 1. Now, I'm going to do 1,000 just because I want it to be a really thorough simulation. So I'm going to fill this all the way down. I think I started on 5, so I'm going to go to 1,005 or 1,004, and just to make sure I got 1,000 there, I'm going to count them. Remember, count itself only counts numbers, so if I go A1 to A1004, oh, 999, I need one more here. Okay, now if I count to 1,005, yep, I got 1,000. Okay, so I can delete that. So I got my 1,000. I'm A6. I was off one. Okay, A6 to A1005. I've got my random numbers. Now, how do we convert that to demand figures? Well, we're basically saying we've got numbers between 0 and 1 here. Well, those are like probabilities, right? Remember how we go from a probability to a value in a normal distribution with given parameters? Yeah, it's the inverse distribution function. So it's norm.inv, the probability, that's going to be our random generated number. And then the mean and standard deviation, we'll use cell reference here, are going to be our known distribution of cookie demand. So the mean is 200. Now, however, I'm going to be sliding to fill this, so I don't want the mean to ever change. So I'm going to lock that reference in, C $1. And then likewise for the standard deviation, that's going to be C $2. So we know then as we fill this, we'll be using the same mean and sigma for every time, but we'll be using a different randomly generated probability value. And we'll call this simulated demand. It'll give us a nice representation of the distribution with these parameters. Okay, so we've calculated our simulated demand, and every time you enter another function, or you can just press F2, enter, we get a new set of random numbers. Now, all that's left to do really is calculate profitability. But to calculate profitability, we have to dial in a production value. So I'm going to create another box up here. I'm going to use this for cell reference. I'm going to call it production, and we'll just start at the average. We'll play with this. Let's start at 200, and now we can calculate profit. Okay, so let's work out kind of logically in our head, and I initially did this on just a piece of paper with pencil, and I'm going to show you the logic I worked through just writing here on Excel before I try to set up the equation, because it's going to be a pretty hairy looking equation. So I want to think about it this way. Profit is going to be, we're selling them for $1.25. I'm looking at per unit revenue minus expenses or the cost, and that was 50 cents. So that's 75 cents per cookie. But that's only for the ones we sell. Okay. So the thing is, we're going to make 75 cents a cookie if demand is greater than production, right? We have to make this production decision each morning. That's what this box right here is going to represent. And then profit's going to depend on whether the actual demand is greater than that or not. So if actual demand is greater than that, like here down here in this simulated value, yep, we're selling all 200, so we're making 200 times 75 cents, $150. Okay, that'll work out to $150. But if we're only selling 161, we're going to make 161 times 75 cents, but then we're going to lose 10 cents on the 39 that we don't sell today. All right, so this is going to be the result. This is going to be a conditional calculation. And what it's going to depend on, and what we'll actually do in Excel, is we'll say if the demand, which is B6, is greater than the production, which is C3, and I'm going to indicate that we need a $sign there to lock that. If B6 is greater than C3, then we're going to make 75 cents times C3. And if it's not, we're going to make 75 cents times the actual demand, B6, minus the 10 cents times the difference between what we produce and what we sell. So that's C3 minus B6. 10 cents times C3 minus B6. This is what we have to now convert into Excel formula logic. But we'll kind of hold this over here as a reference, and we'll see if we can do that. Okay, so profit. It's an if function. Logical test. So the test is B6 greater than C $3. B6, that's my simulated demand again, remember. If that's greater than C3. Okay, I was off one over here, C3. If that's the case, I'm going to wind up making a profit of, and put this in parentheses, 0.75 cents per cookie times the number of cookies I produce, which is C3. C $3. I'm going to be filling this 1,000 times. I gotta lock my cell references for the fixed values, which is the production here. Okay, so I can close the parentheses. That part's easy. Okay, so what we just did represents our profit if demand is equal to or greater than what we produce. But What if it's the case that actual demand, which we're simulating down here, is not equal to what we produce? Well, we are still going to make, I'll put this in parentheses, we are still going to make 75 cents times the actual demand. So the ones that are actually bought, we make 75 cents on. Right? But we're going to have to subtract out the fact that for each one we don't sell today, we lose 10 cents. And how many do we not sell today? Well, that's only if the simulated demand is less than what we produce, and it's the difference between what we produce and simulated demand. So that's going to be what we produce, C $3, minus actual demand, B6, times the 10 cents we lose on those. And I think I need to add one more parentheses here. Yes, I want to group that. Okay, so it's this minus this. And I think I can now close out all my parentheses, and I should be good to go. C3 minus B6 times 0.10. Okay, I see my error here. Instead of 10 cents, I've got $10. Forgot a decimal. Okay, fix my error there. There we go. Now when I recalculated, all my values are above 300. But let's just go ahead and fill this all the way down. And you'll see that when the simulated demand is less than 200, my profit is well less than 150, because I'm making my 75 cents per cookie on the 123 here, but then I'm losing 10 cents per cookie on the 77 here that I didn't sell today. So that nets out to 84.54. Okay, so I'm going to underline this. Now over here I'm going to start thinking about, okay, we're going to run this simulation a lot. And just press F2, enter as many times as we need to, at some different values of production, and we're just kind of take the central tendency of the estimated profits and make a table of them, and then find whichever one's the largest, and that'll be our target production level for any given day. Okay, so, and we're producing the cookies in batches of a dozen. So, and let's kind of take the mean. Let's start at the mean, or the value in dozens closest to that. Let's go a couple dozens down, a couple dozens up, just as our baseline, and we'll run the simulation at all those levels and see if we can find optimal profit. So I'm going to do over here, so I'm going to say simulated production levels, and to make life a little simpler on me, I'm going to put it in dozens, and instead of 200 now, I'm just going to put equals 12 times cell references. Okay, so, and I created a reference value, and let's do E5. So E5, I'm going to start putting dozen numbers in there. So 200 divided by 12, 16. Let's start with, say, 14 dozen. Possible profits. Okay, I get the maximum I can get is 126. But then I can also get $30, $40 on a really bad day. So anyway, what we want to do is say, what's the average profit? Actually, what I want to do here, I'm going to put some space in here. What I want to do here is do simulation. I'm going to do 1 through 10. I'm going to run each simulation 10 times. Then I'm going to find the average profit for each time. And then over here, what I'm going to do is copy them down. And then I'm going to take the average of the averages. So I'm going to call this average estimated profit. Okay, so I've set up this little table here. And what I'm going to do is I'm going to run the simulation 10 times at a level of 14 dozen and see what average profits are, and then I'm going to average the averages. And I'm going to do the same thing for 15 dozen. Then I'm going to do the same thing for 16 dozen, 17 dozen, 18 dozen. Let's see, 18 dozen. That's 216. Yeah, let's maybe do 19 and 20 dozen. So we're going to run this simulation a lot of times and see what kind of results we get for average profits. Okay, and the reason I have to average the averages is because I will have some range, I'll have some variability in my average on each simulation. But as I average averages, I'll actually get pretty close to what we call the population mean. As the more samples I take, taking the average of the sample averages actually gets me closer and closer to the population average per some complex math known as the central limit theorem. But anyway, we don't need to get into that. Let's just do it. So average profit is going to be average of the potential profit outcomes in C6 through C1005. That's all 1,000 simulated values. Okay, so my first one is 117.14. And I could type that in or just paste the value. If I type it in, when I hit enter, it gives me it runs my next simulation for me. So I got 116.03, 116. Okay, so I did that 10 times. As you can see, I generated my different simulated demand per my distribution 10 times. And I'm going to average out my averages, average of this range right here. So I'm pretty confident that my population average for a production run of 14 dozen is $116.71. Okay, same thing now at 15 dozen, and I'm just going to put production now equals 12 times H5. So there's 15 dozen, 180. And I'm going to type in my average results from here. 122.68. Okay, now I'll take my average of those by just dragging that average formula over. And now I'm up to 100. I'm pretty confident that I'm averaging something around $122. So profits go up on average, moving from 14 to 15 dozen. Let's see if they keep going up, moving to 16 dozen. So now let's run 12 times I5, 12 times 16, or 192. Okay, and I got a new average profit now, 125.64. Okay, so I've run that 10 times, and my values are in the 125 to 127-ish range, but let's just average them. Okay, 126.84. Hey, profits are going up more. Okay, profits are up about $5 on average, so 16 is better than 15. Let's see if 17 is better than 16. So let's now put 17, J5, which would be 204 cookies. And I'll type in my averages, 130.25. Okay, so I have 10 estimated average profits at 17 dozen. Let's average all of them out, and I'm at 130.88. So profits are up again. So we're going to keep doing this. I'm going to put it 18 dozen in. Okay, and then find the average of the averages. And I'm going to keep doing this as long as this number keeps rising. And once this number stops rising, I'll probably do another dozen or two and just to confirm that it's back on a downtrend. And then I'll realize, yep, I have peaked at my expected profitability at that level of production. So that was 18 dozen. Let's move on and try 19 dozen. Okay, my values are ranging in the 135, 6, 7, so I'm thinking my average of those might be even higher. And yep, it's 136.27. Okay, so let's keep going. Let's try our 20 dozen. Average those out, 138. I'm still increasing in profit. So let's extend this table over. Let's try 21 and 22. Dozen. Let's see if we keep going up. Okay, and I've run that 10 times. And now, okay, indeed, my average of my averages has declined. And let me just to confirm that, just make sure that's not a freak of sampling, I'll run one more. I'll run it at 25 dozen. And that's 300 cookies. And now let's plug some numbers in. 137.11. Okay, and my average is 139.08. So I think we've established now that this is now trending downward, and my peak value right in here at 139.69, 23 dozen. Right, so we're going to be best off in this operation making 23 dozen, and our long run expectation of profits based on the fact that this distribution of daily demands doesn't change, it's going to be $139.69. Now, no, there's not much difference if we go 1 dozen plus or minus, but if we just produce the 200 cookies, which is about 17 dozen, we're talking about a difference in profits of $9 a day. And if this bakery operates 300 days a year, we're talking about a difference in profits of $2,700. So that's nothing to sneeze at. If you didn't have the ability to run this simulation and do this kind of estimate, and you just said, well, we'll produce the mean every day, and we'll produce 17 dozen, you're talking about something that adds up over time. Okay, so we're moving on in homework 3 now with the binomial distribution problems, and we'll just do 3 of these. They should be pretty quick. Starting with 521, which is on page 204 if you want to follow along. And it says this: many vehicles used in space travel are constructed with redundant systems to protect flight crews and their valuable equipment. In other words, backup systems are included within many vehicle components so that if one or more systems fail, backup systems will assure the safe operation of the given component and thus the entire vehicle. It's called redundancy. Okay, and it says, for example, consider one particular component of the U.S. space shuttle that has n duplicated systems. That is, one original system, n minus 1 backup systems. Each of these systems functions independently of the others with probability of 0.98, 98%. This shuttle component functions successfully provided that at least one of the n systems functions properly. So, set up a few things here. I'm going to put the n in first, which is and then the probability of success for the system. And then over here we're going to think about using a binomial distribution to calculate some outcomes, which says n equals 2. The probability is always going to equal 0.98, the probability of success. And that, for outcomes, I want to think about actually failure first. The hardest thing about these problems is actually setting them up. And as I was kind of practicing this problem, I realized that you really need to think about the outcome of failure first, and then think about success in light of that. So let me show you what I mean. So we can, failure or success. So it's definitely a binomial situation, isn't it? So binomial distribution. Number of successes. Well, this is failure, so failure would be 0 successes, right? We're thinking about the outcome of 0 successes in 2 trials, where each trial has a 98% probability of success, and we want to find out the probability of exactly 0 successes, so that's going to be a 0 false, and it's 0.0004. So there's a 0.0004% chance. We could put it into percent. Let's add 2 decimals. 0.04% chance that it fails. What's the chance that it succeeds? Meaning at least one of these things works. Well, that simply equals 1 minus that. So here we got a 99.96. Okay. And then we can just do the same thing when we go to the 4 backups with the same probability of success. Just drag my formula down. Now that's 0. That's essentially 0. And we're going to have a 1. We're going to have 1 until we really show some decimals here. Boy, we're going to have to show a lot of decimals. There we go. 99.99998. That's pretty good if we have 4 backups. And all we needed, it says in problem C, part C rather, this is B. It says, what is the minimum number of duplicated systems that must be incorporated into the shuttle component to ensure a 0.9999? So 3 gives us a 99.99, and actually I think that's what the question was looking for, because if we take that out of percent, that's 0.99999, so that's more than 0.9999% chance. So 3 actually does it. 4 is overdoing it. 3 actually does it. So you see here the problem was actually pretty easy to work. The difficulty is just knowing how to set it up and knowing how to apply that binom.dist Excel function properly. Okay, now problem 536 is one for you to do on your own. It's pretty much the exact same problem. Let me just give you a hint, a pointer, in how do you set it up. Okay, you want to think about the number of questions, that's your n, the probability of a correct guess, and then run some binomial distributions. Think about 2 different outcomes. One is the outcome of getting a score of 0, and thinking about how many successes would that be in terms of the probability of guessing correctly. That would be 0 successes, right? And then the non-zero score would be anything other than the 0 score, so 1 minus the result you get here. And then basically all you need to do is say how many questions you need to have. You can start at 1 and just keep tacking on questions and keep, the probability is going to stay 0.2 the whole time, and then keep running these, drag these down to see until you get to where the outcome of a 0 score is pretty assured. Problem 527, I'm on page 205. It says, assume that, on average, 95% of all ticket holders show up for a flight. If a plane seats 200 people, how many tickets should be sold to make the chance of an overbooked flight as close as possible to 5%? So we all know that airlines do this, and I've actually been bumped a few times. They pay you, $200-300 a flight voucher, and it's worth it if you're not in a hurry. In many cases, they sell more seats than the plane has because they know that a certain number of people will miss the plane. They're trying to max out the passengers. The marginal cost is essentially 0. So extra passengers, once they get nearly full, extra passengers are pure profit. So they want to max that out. There's a small risk of overbooking that they're willing to accept. Okay, here's the way I'm going to set it up. Put a title in, and basically want my N and P. We always want those, and I've just kind of described what those are down here, the number of seats, and whether people will show up or not. Then the tickets sold, and then what's the chances of that the tickets sold is going to be greater than the number of seats. So let's fill everything in. Okay, so my number of seats available is always going to be 200. My probability of people showing up is always going to be 0.95. The number of tickets sold is a question. Now, where do we want to start that? Well, if we start that at 200 and every person individually has a 95% chance of showing up, we would never overbook. So that one's kind of irrelevant. We would never aim to sell 200. It's always going to be something more than 200. So I'm actually going to start at 201. And then to calculate the probability that when selling 201 we overbook, which gets us something greater than 200. Now we can run a binomial distribution to calculate that. So binom.dist, number of successes, is basically going to be the number of seats available plus 1, because all the problem said is what's the probabilities of overbooking, not overbooking by a particular amount. So anything greater than the number of seats available. So we'll just add 1 to it. And we have 201 trials. We have 201 opportunities, an individual 95% chance for the people to show up. Now, of course, this one's going to be extremely rare for all 201 people to show up if each one has a 95% chance. So plug in the probability, and then we're going to go with the 0. And indeed, we see that that's 0.00003. That's less than 1,000th of a percent chance. So what I want to do now is start ramping up the number of tickets sold. I'm going to keep everything else the same, and I'm going to ramp up the number of tickets sold, and you'll notice that if I grab this whole chunk here, Excel's going to autofill and increase the number of tickets sold, but it's going to keep everything else the same. Okay, so 200 seats available, 95% chance each time of people showing up, and now we're going to ratchet up the tickets sold one at a time. And then I'm just going to fill the formula down. And the problem said, remember, how many tickets should be sold to make the chance of an overbooked flight as close as possible to 5%? Well, now all we need to do, and let's put this as percent, is find the ticket sale number that's close as it can be to 5%, and that occurs right here. 207 tickets are sold, and there's a 5.28% chance that at least 201 of those 207 ticket holders will show up, and hence we'll have an overbooked flight. Okay, let's wrap up on a pretty easy one. Problem 529 now, which is on page 206. And it's really simple. It says a firm's office contains 150 PCs. The probability that a given PC will not work on a given day is 0.05. So this time we'll just have a real simple setup. N, P, and then the outcome. N is the 150 PCs, computers. Probability of any one failing on a given day is 0.05. Okay, and then the outcome, of course, is what we'll calculate based on the scenario that the book sets forth. So part A says, on a given day, what is the probability that exactly one computer will not be working? This is easy. Binom.dist. We want the outcome here as failure, and we're interested in the number of successes, not the number of outcomes, 1, out of 150 trials with an individual probability of 0.05. We want exactly that outcome. So it's 0 for false. and that is 0.003596, or if you prefer, a 0.36% chance. Okay, then B says, on a given day, what is the probability that at least 2 computers will not be working? Well, we can fill this in. We know the individual probability and the number. But for the outcome, this one's a little tricky, actually. Let me grab a blank page here. I want to draw a picture just to help me set this up. Okay, I want to think about my distribution of failures. My probability of failure is 0.05. My N is 150. So I want to first off calculate my mean, my expected number of failures. That, of course, is N times P. N times the P of 0.5. So that's 7.5. And then I actually also want to calculate my plus and minus 1 sigma. So sigma, you'll recall, is the square root of N times P minus 1. So let's go ahead and run that through the calculator as well. Of course, we know that N times P is 7.5. So 7.5 times P minus 1, that's going to be 0.95. 7.125, then I want to take the square root of that. So my sigma is, let's call it 2.67. Sigma equals 2.67. And then I'll add that to 7.5 and subtract it from 7.5. And this is approximately normal. I've got, about 68% of the times we'll have between 4 and 10 computers failing on a given day. This is saying, on a given day, what is the probability that at least 2 computers will not be working? At least 2. So let's find 2 out here. And what's the probability at or greater than that? Let's pick a different color here. Let's highlight. So basically the area under the curve to the right of 2. Now, I can't calculate that directly, but I could calculate the area to the left of 2 and then subtract that from 1, and that would give me the remaining area. But now here's the catch. We're saying, what's the probability that at least 2 are failed? Okay, at least 2. That's going to equal the probability of 1 minus strictly less than 2, and because we're working with integer data here, we have to go to 1. So 1 minus the probability that less than 1 is fail. So this is how I'm going to set up the binomial problem in Excel. 1 minus the binom dist of strictly less than 1 or strictly 1 failure. And that'll give me this area in the yellow to the right of that critical value right there. Okay, so let's go ahead and enter that in, punch that in. 1 minus binom dist. Number of successes is now just 1. The trials is 150. And probability, of course, is a constant 0.05. And we're looking for false. I forgot to add a parenthesis. Okay, Excel added it for me. So that's what it looks like. And probability-wise, we're dealing with 99.64. There's a really, really, really good chance that we're going to have 2 or more computers failing. Well, that makes sense when you look at our mean. Remember, our mean, we're expecting 7.5 a day, and our empirical rule said, 2/3 of the time we're going to have between 4 and 10. So it's a really, really good chance that it's going to be greater than 2. And it's exactly what we worked out here. 99.64. Now the only other thing this problem asks is, what assumptions do your answers in part A and B require? Do you think they are reasonable? Well, we're assuming always with binomial distributions that the success rate, in this case the failure rate, the events are not related, they're independent. And that might not be realistic in a office computer situation, especially think about the computers are all networked, and if something goes wrong with the network, that might cause problems for multiple computers. So failures might be kind of positively correlated in that office setting. But nonetheless, binomial distribution is still a really useful tool to think about how to structure these kind of problems and to think about probabilities of these kind of contingent events happening.